This is Hongwei Zhang. Today I'm going to discuss our effort on the platforms and infrastructures for collaborative open innovation in connected and automated vehicles. So this is a joint work with many colleagues, including my colleague Jing Hua and our team members Yue Hua, Hai, Chuan, as well as other collaborators and team members who I will mention at the end of the discussion here. So the broad context for this effort is the road transportation. So if you look at the road transportation today, we actually face daunting challenges in many ways. For example, if you look at safety, every year across the world we have about 1.4 million fatalities and over 50 million injuries. And then the accidents alone causes about 25% of the traffic congestion we see today. So that's about safety. Now if you look at environment, pollution and energy use, we also have significant challenges. For example, the road transportation accounts for about 20% of the world's energy use and 60% of the world's ozone pollution today. In terms of efficiency, there's congestion remains a big challenge in many cities. For example, in U.S. alone, about 4.2 billion hours of annual travel delays introduced because of congestion. Now, in order to address these grand challenges in transportation, it's expected that the transportation systems and the vehicle systems are going to undergo fundamental transformations in the coming years and decades. And one transformation that's actually taking place is the transition from the traditional single vehicle based control to networked vehicle control. So the basic idea is that instead of just looking at each vehicle as an individual entity, we try to treat each vehicle as a part of the transportation ecosystem and then see how we can optimize the behavior of the system as well as the individual vehicles and effectively. In this context, there are many canonical examples of the applications of this new paradigm. So one application is active safety, where the key idea is to enable vehicles to communicate with each other so that they don't collide with each other. It's expected that this alone can eliminate up to 90% of accidents we see today, which almost means more than 1 million people's lives saved per year, as well as big savings in terms of the costs associated with accidents. Now, to enable this, to realize this vision, there has been active effort across the world in U.S., Europe, Asia. For example, in U.S., there's the industry consortium, the CAMP industry consortium, that have been actively investigating the active safety, and then U.S. DOT has also initiated several efforts trying to help moving this field forward. This include the large-scale safety pilot that was done back in 1 or 2 years ago, and also the U.S. DOT is planning for really large-scale pilot deployments across USA in the coming years. There have also been many test beds that have been established by U.S. DOT. So that's in the area of safety. Now, if you look at the energy aspect, the fuel economy of vehicles, in the past 100 years, the main focus has been on how to design and operate individual vehicles so that we can maximize fuel economy. There has been a lot of innovation happen in that direction, but we more or less actually reached the limit to some extent. So therefore, one of the new direction that's being explored right now is to look into how we can have vehicles collaborate with each other and collaborate with transportation infrastructures so that we can optimize the system, the system-wide fuel economy. So there has been effort looking into how to leverage the concept of vehicle platoon to improve fuel economy. There have been field trials in Europe, for example, and then in US there are also emerging field trials. There are also field trials being planned for the near future. And in the current field trials, it was observed that with very simple strategies, for example, just by having the following vehicles follow exactly what the lead vehicle does, and then try to minimize the inter-vehicle space, we can actually save a lot in terms of fuel. For example, it was observed that somewhere between 8% to 16% of savings can be enabled in fuel consumption. I mean, savings in fuel consumption can be enabled through simple strategies. And then, besides vehicle platooning, there are many other ways you can actually leverage the network information to optimize fuel economy. For example, you can control the optimize vehicle driving strategy based on the road condition as well as the status of the traffic light. Those are just a few examples. Now, so to help realize this vision, there has been active research in many disciplines, in transportation, in wireless communication, in vehicle control, and so on. There have been enormous amount of new ideas being proposed in the past years and decade. So as part of the research process, the experimentation actually becomes an integral part of the innovation process because of the complexity of the vehicle system we're looking at, the networked vehicle systems that involve road, vehicles, and traffic, other traffic infrastructures such as traffic lights. So we have been actually looking to the experimentation aspect of connected and automated vehicles as part of the NSF Global Environment for Network Innovations program, where the goal is to look into how we can develop and establish open innovation infrastructures to help facilitate the experimentation at scale and at high fidelity. So, when talking about experimentation effort, experimentation infrastructure effort, we have been actually involved in this area for many years. For example, we have developed and have been running the NetEye wireless sensor network testbed for many years. The testbed is also actually widely used by researchers across the world. So this is something that's pretty much actually mature today. Like if you think about experimentation in wireless sensor networks, but when we think about experimentation in networked vehicle systems, we still face grand challenges today. Actually, the very first challenge was how to really enable cross-discipline collaboration, cross-discipline open collaboration in the domain of connected and automated vehicles. Part of the challenge is actually the lack of shared experimentation infrastructure right now, right? So if you look at today, we don't have an experimentation infrastructure that can be leveraged by all the involved disciplines of connected and automated vehicles. For example, we don't have an infrastructure in which a single infrastructure in which you can not only study the issues related to transportation in the context of connected and automated vehicles, but you can also do research and experimentation in the, for example, networked vehicle control and wireless communication aspects. So the lack of shared experimentation infrastructure makes it a little bit more difficult to for different disciplines to be deeply engaged in the early innovation process. That's one drawback. Another potential drawback of this approach is that this make it the lack of shared infrastructure also makes it difficult to deploy to do experimentation at really high scale for different communities. For example, it's conceivably difficult for each community to deploy tens of or hundreds of thousands of vehicles to run experimentation for themselves without sharing the infrastructure. So therefore, the very first challenge is actually how to have a shared experimentation infrastructure upon which different communities can be deeply engaged early on in the innovation process, and then be able to share resources and do experiment at scale at the same time. So that's the very first challenge. The second challenge is that it's expected that the technologies and applications of connected and automated vehicles will continuously evolve, and the cycle of evolution will be much shorter than the lifetime of vehicles in general, and may even be shorter than the lifetime of a large-scale testbed. So there's a question of, can we actually continuously evolve the capability of the testbed or experimentation infrastructure in general, without having to redeploy equipment in a testbed or experimentation infrastructure. So that's a second challenge. The third challenge is that usually the vehicles are actually safety critical, so therefore they are actually traditionally closed. And for example, if you look at today, it's pretty difficult for students, researchers to change the behavior of their vehicle, or even just to monitor the status of the vehicle operation in a real-world settings, without having to really have deep collaboration relation with the automotive industry. So in order to help address these challenges, we have been working on an NSF Genie project where we look at different elements of the solutions that may well contribute to the solving some of these challenges. So the first capability that we're developing is the software-defined platform virtualization, where the basic goal is to enable concurrent, non-interfering access to the same physical platform by different communities at the same time. So for example, given a physical platform, we can actually virtualize it into different slices. For example, different virtual machines. Maybe in this example, there could be a virtual machine for the transportation community, and there may be another virtual machine for the wireless communication community. In this way, we could have two communities share the same physical platform, but without interfering with one another, using the technique of software-defined virtualization or partition of the resource. Now, when we think about the virtualization of the platform and infrastructure, so one key aspect is how to virtualize the wireless networking and vehicular sensing resources. So this is some of the new capabilities we're developing right now, and it will be ready by the end of 2014. So it's expected that by the end of 2014 we're going to have the technique and platform for software-defined virtualization and partition of the experimentation resources. With this capability, we will have a platform that can be deployed in field, and then this platform can be used by different communities, different disciplines to do experiment, to run applications at the same time, but without interfering with one another. Now the second aspect is software-defined radio, which can enable software-defined innovation evolution. So the motivation for this is as follows. As we have seen, if you look at the applications of connected and automated vehicles, we are actually looking at a spectrum of applications that will be gradually deployed over time, and these applications will have increasingly more demanding requirement about the inter-vehicle communication, or in general V2X communication, V2X wireless communication. So therefore, it's expected that the underlying wireless communication technology itself will evolve over time. For example, maybe evolving from the current version of DSRC that's good for the warning applications to the next version that may be a very good foundation for actually enable the fully automated operation of the vehicle flows, vehicle platoons on the road. So therefore, there's a question of how do we enable this evolution. So the idea we have here is to leverage the software-defined radio such that with a single deployment of the physical platform, we can evolve the protocols that's running inside the platform using software alone without having to change the physical deployment. That is, just have one physical deployment, we can actually evolve the capability of the physical platforms deployed, as well as, for example, the protocols running in those platforms using software alone without having to change the hardware. So that's one benefit in terms of enabling the evolution. Another benefit is that as the different versions, as technology evolves, we want to be able to test compatibility and interoperability between different versions of technology, right? So therefore, by having the software-defined radio, we could even have multiple versions of for example, the DSRC running in a single radio, and then be able to check all those issues that's related to the evolution of technology. And then the third aspect of our platform is to think about how to open up the traditionally closed vehicle systems so that the broader community can be engaged in the research, application, and education of connected vehicle systems. Now, in this context, we have two sub-efforts. One effort is by collaborating with colleagues at Ford Research, looking into how to integrate OpenXC into our system so that we can enable internal sensing of vehicles. For example, you can get real-time information about vehicle internal state, such as the engine status, the transmission status, the fuel consumption, the emission, and so on. So that's about internal vehicle sensing. Now, in the meantime, we're working with Professor Zhang in integrating the camera-based external sensing, basically using camera as a media to sense the surroundings of vehicles. So, for example, detecting surrounding vehicles, pedestrians, and so on. Now, these three aspects of the new capabilities of our platform is currently being developed, and most of them, I think actually all of them will be ready by the end of 2014 or early 2015. Now, as a way of validating our design, and also as a way of showcasing the benefits of having open collaborative innovation platform deployment, we are going to actually deploy somewhere between 5 to 10 or slightly more number of such open innovation platform into our campus police patrol vehicles. Now, after the deployment, each platform will be partitioned into two slices. One slice will be used by our campus police for doing live online 3D campus patrol, so that they can, no matter where they are, they can actually get to see real 3D status of the campus, which can greatly help with their patrol mission. And the other slice will be used by actual wireless researchers to run large-scale emulation of connected or networked vehicles. So the idea is to, in this latter respect, the idea is to integrate the small-scale deployment on campus with large-scale flexible emulation of network vehicles in the cloud, so that you can get the benefit of the high fidelity of the campus deployment and the scalability, and as well as flexibility of the simulation in the cloud. In particular, in terms of the emulation, the basic idea is to integrate for example, the NS3 emulation of networked vehicle systems in the cloud, as well as the high fidelity simulation of vehicle mobility in the cloud. Integrate those simulation with the campus field deployed open innovation platform, so that we can use the field data to improve the emulation or simulation fidelity in areas such as wireless channel behavior, application traffic behavior, and vehicle mobility. Now let's look at, we actually have made significant progress in all this respect, and here's a short demo that can sort of give you a sense on how the overall system may actually function. So in this demo that you can see, we have one vehicle deployed on campus, and in the vehicle we have a prototype of our open innovation platform. The prototype has been partitioned into two slices. One slice is to run external sensing, for example, using camera to run external sensing, for example, detecting surrounding vehicles. Another slice is to run vehicle internal sensing, the OpenXA-based sensing, and also to run the vehicular sensor and control network emulation in the other slice. So the intention of this is to show the capability of having multiple use of the same physical platform at the same time, but without having the two use cases interfere with one another. And then this in-field platform will be integrated with the NS3 and Sumo-based emulation of networks in the cloud, in our Genie rack, for example, and then be able to see, then we're going to see how, and then using these integrated systems, we're going to see the protocol behavior and the impact of the protocol behavior on application. And then we also have other use cases, basically, to show that you can use this whole system on one hand to run emulation, on the other hand also to do real sensing, for example, the real vehicle detection, fuel economy sensing, and data visualization. So now let's switch our screen and to see how the demo looks like right now. So here what we're seeing is a kind of overview about the different screens that we're going to show you in detail later. In this demo, basically we're going to show you the road view, and then the emulation systems, and then the fuel economy sensing, as well as the vehicle detection and the data visualization. So let's first look at, so they get a sense of where the demo happens and how it looks like. Basically, we have involved one vehicle is equipped with the OpenXA, the Open Innovation Platform we just talked about, and then the other vehicle is driving in front of the vehicle equipped with the Open Innovation Platform sort of environment, like the surrounding vehicles that's to be detected by the Open Innovation Platform. The vehicle that has Open Innovation Platform, we have basically the platform deployed, including what you see here, the GPS, and then the antenna for the V2X communication module, for example, the WiMAX dongle, and as well as other communication modules. And then we also have some laptop that actually monitors the sensing result that we're going to show. So let's first look at the emulation system. Now, in this emulation system, we have a number of vehicles, for example, 20 vehicles simulated in the cloud. And then one of those virtual simulated vehicles will be mapped into with the vehicle deployed in field. So it's just like in the simulation, in the emulation, we have one real vehicle, real world vehicle that's interacting with the other 19 simulated vehicles. So in this demonstration, the emulation we're going to show you is the sharing of vehicle internal state. So for example, we may one of the vehicle, the actual real vehicle, will share its speed information with another simulated vehicles, where in the simulation the two vehicles are actually very close by, so that the other vehicle may want to know the speed information of these real-world deployed vehicles. So what you see here is, one window is showing the OpenX sensing data, which include all kinds of parameters such as speed, torque, steering wheel angle, engine speed, and so on. So, but then we're going to extract one specific parameter, the speed information, and then integrate that with the NS3 emulation in the cloud. So this is just some procedure we're following to get the emulation started. So the data is already coming, and then in the other window you see that so the vehicles are added into the emulation. So one of them is actually the real-world vehicle that's going to interact with other 39 simulated vehicles. Now in the visualization, what we're showing here is the ground truth, the actual speed of the real-world vehicle, and then we're going to see using the current DSRC wireless communication. You can see here, the ground truth data. Ground truth data basically shows the actual speed. The received data here shows the perceived speed by the other simulated vehicle. As you can see here, most of the time, the ground truth and the actual perceived speed is actually matches with each other very well. But once in a while, the packet may get lost or may be delayed, so that the perceived speed is actually different from the actual speed, and the difference may be high, but may be low, but may also be quite high. So therefore, as you can see here, the current DSRC actually works well in most cases, but once in a while there may be unexpected behaviors. So therefore, I think probably it's actually a very good technology that may be well suited for the expected near-term deployment of warning applications, for example, active safety-related warning applications. But if we want to really enable autonomous control of vehicles, or semi-autonomous or human-in-the-loop control of vehicles, there are actually room for improvement in the technology itself. And as you may well know, there has been already effort going on trying to improve the technology itself. So that's the emulation. So with that, we hope to show you that with the Open Innovation Platform and the setup of the system, you can actually extract the real-world vehicle data and then integrate that with large-scale simulation in the cloud to enable flexible at-scale emulation of vehicular network and vehicular sensor and control networks. So next, let's look at the potential use of our Open Innovation Platform for developing, some developing applications. Actually, for example, you may, one toy application could be to detect fuel economy. Like you want to detect fuel economy, so that you can potentially model the fuel economy of vehicles, and then based on the model, you can control the vehicle systems to optimize the fuel economy. So here we saw the different type of OpenXC data that's been received, and then based on the data, we can actually analyze the real-time fuel economy of the vehicles. For example, based on the distance traveled and the fuel consumed for the specific distance traveled, we can compute the instantaneous fuel economy which is shown by the blue line here. And then based on the instantaneous fuel economy, you can also analyze, for example, the average, the long-term average, based on the average of the fuel economy over time, which is shown in the purple line here. We also shown other vehicle parameters such as vehicle speed and so on. So if you look at the data here, you can actually see the correlation between the fuel economy and the vehicle speed. In many cases, as the vehicle speed increases, the fuel economy also increases. So that's about the vehicle fuel economy sensing. Now, another type of real-world application that you can think about is actually the vehicle detection. Camera-based vehicle detection is, we have this vehicle equipped with open innovation platform. Part of the platform is this camera and then the related software for doing vehicle detection. Now, on the screen to the left, here you see the real-time detection result. For example, if the vehicle is detected, we would show kind of a yellow brownish box here. Inside the box, we show the estimated distance between the vehicles, between the leading vehicle and the vehicle equipped with the open innovation platform. So you see the live real-time tracking of the inter-vehicle distance here. So next, let's look at data visualization. For example, a virtual gauge. So here we showed, from this, here you can see that we can actually show the live data about the engine speed, fuel level, odometer, and vehicle speed. So the live data is coming from the deployed vehicle, and then we can show it on this virtual gauge here. You see the engine speed is changing a lot. The fuel level and odometer doesn't change as fast as you could imagine, but the engine speed and the vehicle speed is, you do see this quick change, potential quick change over time. Now in this short demo we showed how we can actually partition the same physical platform into two slices, one used for vehicle detection, another used for wireless network emulation. So that's one aspect. But we also hope to have shown that with this platform you can also develop higher layer applications such as object vehicle detection, also for data visualization and so on. But essentially with this platform, access to the different kind of vehicle data so that you can use the data to drive any application development. To summarize, as we see, there's great challenge associated with road transportation today, and one part of the solution to those grand challenges is actually the networked vehicle control systems or networked traffic networked transportation systems. Now, to really help realize the vision of networked vehicle operation or networked transportation systems, we need different disciplines or different communities of the networked vehicle systems to really collaborate with each other in a way that going beyond the traditional way how we collaborate. For example, the traditional sequential innovation process. We need a better, a more collaborative open innovation process, open parallel innovation process across disciplines in the networked vehicle systems. Now, to support this collaboration, we actually need platforms and experimental infrastructures that can truly support the collaborative open innovation across disciplines. With that, we hope to be able to enable the continuous rollout of different technologies and applications that will help solve the grand challenges of transportation today. Now, before I conclude, I would like to mention a few other infrastructure that we have been operating and also been actively extending in the coming years. So one infrastructure is the NSF Genie WiMAX, or Cellular Research Network in Detroit, which is deployed on the rooftop of our department building. The network actually covers the midtown of Detroit as well as part of downtown Detroit, and all the highways around the midtown Detroit, including I-75, 94, and Michigan 10 Speedway. So another infrastructure is the cloud computing infrastructure that's deployed in our campus, which is a part of the national high-performance computing cloud infrastructure. Now this can be used for many of not only for large-scale network emulation, but also potentially for big data research related to in the domain of connected and automated vehicles. So I would also like to acknowledge the support and by the NSF Genie program. It is with their support that we can get a chance to work on, pursue the effort in this connected in the open collaborative innovation platform and infrastructure for connected and automated vehicles. We would also like to thank the many initiatives and many colleagues in the US DOT and Michigan DOT communities. It is actually by working with them we get to see the need for such open collaborative innovation platform. Therefore, our current effort trying to build and deploy these platforms. So at Wayne State University, we also had the pleasure of working with many other colleagues, including our long-term friend and collaborator Dr. Patrick Gosman, also our police chief, Mr. Anthony Tony Holt. We also get tremendous support from many other colleagues such as Matt, Brian, Andy, as well as our lab team members Yu, Pengfei, and Lin, etc. So beyond outside Wayne State, we also have this effort is actually also enabled by collaboration with many other institutions outside Wayne State University. In particular, we would like to thank the support and help and the collaboration by our colleagues from Ford Research. So in the past many years, we have been working together on these and similar initiatives. Also, we'd like to thank Professor George Riley at Georgia Tech in helping us with the necessary emulation and parallel simulation effort. Professor Weidong Zhang from University of Michigan Dearborn in helping with the software-defined radio initiative. Also our colleagues in China from Tongji University, Jiangsu University in exploring the collaboration in this domain, and also the potential of deploying these open innovation platforms in some of the research initiatives in China. So we also thank the support by the Merit Networks who help with our exogenous cloud computing infrastructure, as well as many other networking experiments. So we are actually right now looking for partners in realize the vision of large-scale open innovation platform and experimental infrastructure for connected and automated vehicles. In particular, we are looking for opportunities of deploying these open innovation platforms to enable permanent experimental infrastructure that can enable the open collaborative innovation across disciplines in connected and automated vehicle. So if you're interested, please feel free to contact us contact myself or my colleagues at Wayne State University. So here's my contact information. I look forward to the opportunity of working with you. Thank you.